Welcome to Late Night History. Tonight, we are going to travel somewhere no one has ever been. Not a lost city, not a sunken ship, not a forgotten tomb beneath the desert. Somewhere stranger than all of those and far closer. We are going straight down through the floor beneath you, through the foundations of the building, through the soil and the bedrock and the deep, cold stone, down past the limits of everything human hands have ever reached, all the way to the center of the world. And waiting for us there, at the very heart of the planet, is something almost impossible to believe. There is a ball of solid iron at the center of the Earth. It is roughly 1,220 kilometers across in radius, which makes it just a little larger than the dwarf planet Pluto, that small frozen world out at the cold edge of the solar system that we send spacecraft years to reach. Picture that. Picture Pluto hanging in the dark, and then imagine it not out there among the stars, but here, buried under your feet, sitting silently at the core of the planet you are lying on right now, a heart of iron the size of a world, and it is hot. It is so hot that the number almost stops meaning anything. The temperature at the boundary of that inner core is somewhere around 5,400 degrees Celsius. Some estimates put it a little lower, some a little higher, somewhere in the range of 5,000 to 6,000 degrees, but 5,400 is the figure most often given. And here is the thing that makes it land. That is about the same temperature as the surface of the Sun. The surface of the Sun is roughly 5,500 degrees. So there is a place inside the Earth, a place we are walking around on top of every single day without a thought, that is very nearly as hot as the face of the star that lights our sky. Now hold that in your mind, because something does not add up. And the part that does not add up is one of the most beautiful puzzles in all of science. That inner core, as hot as the surface of the Sun, is solid iron. Not molten, not liquid, not glowing soft like metal in a forge, solid like an anvil. How can anything stay solid at the temperature of the surface of the Sun? Iron melts at a fraction of that heat. You could melt iron in a furnace far cooler than the core. So why doesn't the inner core simply turn to liquid and disappear into the rest of the planet? The answer is pressure. Down there, at the center of the Earth, the weight of the entire planet is pressing inward from every direction at once. 6,000 kilometers of rock and metal, all of it pulled down by gravity, all of it pushing toward the middle. The pressure at the very center of the Earth is around 360 gigapascals. That is a number that does almost nothing for the imagination on its own. So let me translate it. It is more than 3 million times the pressure of the atmosphere you are breathing right now, 3 million times the gentle weight of the air resting on your shoulders this very moment, the weight you never notice, the weight that holds the whole sky. And here is what that immense pressure does. It squeezes the iron so hard that it raises the temperature at which iron would melt. Heat wants to pull the atoms apart, to set them loose, to let them flow as a liquid. Pressure wants to lock them together, to crush them into a rigid grid. And at the center of the Earth, the crushing wins. The pressure raises iron's melting point higher than even that solar heat, and so the iron, as hot as the Sun's surface, stays frozen into a solid ball. Think of it as a contest between two enormous forces, heat trying to melt and pressure trying to freeze. And the pressure, by a small but decisive margin, holds the line. That solid heart exists because something is crushing it with the weight of 3 million atmospheres, and not a moment's rest is given. So already we have a wonder. A Pluto-sized ball of solid metal, as hot as a star, kept solid by an unimaginable squeeze, sitting at the very center of the place we call home. But that is only the still center of the story. Because the truly astonishing part is not the solid heart itself. It is what surrounds it and what that surrounding ocean does for every living thing on the surface of the world. Around that solid inner core, there is a vast shell of liquid iron. Liquid iron and nickel, a molten metal sea, roughly 2,200 kilometers thick. It begins about 2,890 kilometers below the surface and reaches down to about 5,150 kilometers, where it meets the solid inner core. This is the outer core, and it is genuinely an ocean. Not water, not lava as we picture lava, but a churning, flowing sea of molten metal, larger in volume than the moon, hidden beneath every continent and every sea you have ever known. It makes up around 30% of the entire mass of the planet. Almost a third of everything the Earth is this hidden ocean of liquid iron, turning slowly in the dark. And that ocean is doing something. It is not still, it is moving, rising and sinking and circling, and as it moves, this metal sea is performing the single most important act of protection in the entire history of the Earth. It is generating a magnetic field, a field that reaches up out of the ground, out past the clouds, out past the orbits of the satellites, out tens of thousands of kilometers into space, where it stands as an invisible shield between us and the sun. That field is the only reason you are alive to hear this. That field is the reason there is air to breathe and water to drink, and a sky that is blue instead of dead. We have a name for the machine that makes it. We call it the geodynamo, the spinning iron engine at the center of the Earth. And tonight, slowly, without hurry, with all the time in the world, that is the story we are going to sink into. The story of how a planet builds a magnet out of molten metal, how a sea of liquid iron, freezing onto a solid heart the size of Pluto, throws up a shield that has kept this world alive for billions of years. Before we go any deeper, let me say a quiet word to you wherever you are. If you would like to, leave a note in the comments and tell me where in the world you are listening from tonight. What city, what country, what corner of the Earth your bed sits in, somewhere above all that iron and stone. I genuinely like to read them, and there is something fitting about it. All of us scattered across the surface of this one shielded planet, drifting off to sleep above the same hidden engine. And if you are new here, and you would like more long, slow journeys like this one to fall asleep to, you can subscribe, and they will find their way to you. That is all. No rush. Settle in. We have a long way down to go, and we are going to take it gently. Now, here is a question that should stop us in our tracks, and it is the question that this whole story has to answer before it can earn your trust. How do we know any of this? How can anyone possibly claim to know the temperature of a place no one has ever been? How can we speak of an ocean of liquid iron, of a solid ball the size of Pluto, of pressures 3 million times the air, when not a single human being has ever laid eyes on the core, has ever touched it, has ever sent so much as a camera or a probe anywhere near it? Because we have not. That is the truth, and it is worth letting it sink in. No one has ever seen the core of the Earth. Not one person, not one drill, not one machine. Everything I have just told you, every number, every degree, every kilometer, was deduced from a distance, the way you might describe a room you have never entered by listening to the echoes from the doorway. Consider how far down we are talking. The distance from the surface to the center of the Earth is about 6,371 kilometers. That is the depth of the journey we are taking tonight. And now consider the deepest hole human beings have ever dug into the planet. It is called the Kola Superdeep Borehole in the far north of Russia, on the Kola Peninsula near the Norwegian border. For years, drilling crews pushed a slender shaft straight down into the crust, deeper than anyone before them, fighting heat and crushing rock the whole way, and they kept going and going, and when at last they stopped, the deepest point they had reached was 12.26 kilometers. 12 kilometers out of more than 6,000. Sit with the smallness of that. If the whole journey to the center of the Earth were the height of a tall adult standing in a doorway, the deepest hole we have ever dug would not even break the skin on the very top of their scalp. It would be a scratch, a faint scratch, on the surface of an apple. The crust we live on, the soil and the bedrock, the part of the Earth we think of as solid ground, the part that holds our cities and our roots and our buried dead, is the thinnest possible skin over a vast hidden interior we will quite likely never reach. The Kola hole, the proudest descent in the history of drilling, the deepest wound humanity has ever pressed into the planet, got barely a fifth of the way through even the crust and stopped there, beaten by heat, thousands of kilometers short of the molten sea and an unfathomable distance short of that solid iron heart. So we have never been there. We never will, not with any tool we currently possess. And yet we know the depth of the boundaries, we know the state of the metal, we know roughly the temperature and the pressure, we know that the inner core is solid and the outer core is liquid, and we know that the liquid is moving.
How? That is a story all its own, and I will give it to you in full a little later in the night, because it is one of the great quiet detective stories of science, a story of earthquakes and shadows and a Danish woman who heard the heart of the earth in the trembling of the ground. For now, simply hold on to the wonder of it. Everything we know about the deepest place on Earth, we learned without ever going there.
We read the inside of the planet the way you might read a sealed letter by holding it to the light. And what that indirect reading tells us, when you piece it all together, is the existence of the engine, the geodynamo. So let me begin to sketch it for you now, gently, the first rough outline, and we will fill in every detail across the hours ahead. Picture again that ocean of liquid iron, 2,200 kilometers thick, wrapped around the solid inner core like the white of an egg around the yolk, except the white is molten metal and the yolk is a frozen ball as hot as the sun. That liquid metal is doing something that liquids do when the bottom is hotter than the top. It is convecting. The hot metal near the inner core rises, the cooler metal up near the rocky mantle sinks, and so the whole ocean turns over, slowly, endlessly, like a pot of soup left simmering on a low flame for billions of years. That is the rising and sinking, the churn. But there is more to it than simple boiling, because the Earth is spinning. The whole planet turns once a day, and that rotation takes the rising and sinking columns of metal and twists them, organizes them, rings them into long spiraling shapes aligned with the axis of the spin. And here is the crucial fact, the fact that makes the whole engine possible. Iron is a metal, and metal conducts electricity. So when you take an electrically conducting fluid and you set it churning and you twist that churning with the spin of a planet, you are doing something extraordinary. You are building a generator, a natural planet-sized electric generator with no wires and no battery and no maker, running on heat and rotation alone. The moving conducting metal generates electric currents. The electric currents generate a magnetic field, and the magnetic field, in turn, acts back upon the moving metal, shaping the currents, which sustain the field, which shapes the currents, in a loop that feeds itself. We call this self-exciting because once it gets going, it keeps itself alive. It needs no spark from outside. It is a magnet that makes itself out of nothing but a freezing sea of iron and the turning of the world. The total electric current circulating down there is estimated to be on the order of 1 billion amperes. 1 billion amperes flowing in great rivers of charge beneath your bed, this very second, silent and unfelt. And now I want to give you the strangest and most humbling fact in this whole opening, the fact that turns the entire story upside down. You would think, given everything I have just described, given an ocean of liquid metal larger than the moon, given 1 billion amperes of current, given a solid heart as hot as the sun, you would think the magnetic field that all of this produces would be tremendously, overwhelmingly strong, a force to flatten mountains. It is not. At the surface of the Earth, where you and I live, the magnetic field is feeble. It averages somewhere between 25 and 65 microtesla, depending on where you stand on the planet. And a microtesla is a tiny unit. To put it plainly, the field that wraps our entire world and holds back the fury of the sun is, at the surface, weaker than a small magnet stuck to your refrigerator door. You have a magnet on your fridge, very likely, holding up a photograph or a child's drawing or a takeaway menu. That little magnet, the cheap one you barely think about, produces a stronger field right up close to it than the Earth's own field does at the surface. Hold a compass near it, and the needle forgets the planet entirely and swings to the fridge. How can that be? How can something so feeble protect an entire world? And this is the second great paradox of the night, the partner to the paradox of the solid heart. The Earth's field is weak, yes, but it is vast. The fridge magnet is strong but tiny, its power dying away within a few centimeters. The Earth's field is gentle but enormous, filling space for tens of thousands of kilometers in every direction, a great soft shield stretched across the whole sky and far beyond it. Strength is not the same as reach. A whisper that fills a cathedral can shape a room that a shout in a closet never could. The Earth does not protect us by being powerful. It protects us by being everywhere, by surrounding the whole planet in a quiet, endless field that the solar wind cannot get past. A feeble magnet, no stronger than the one on your fridge, drawn out across the size of a planet, becomes the difference between a living world and a dead one. So already, before we have gone any deeper, we are holding three impossible-sounding truths at once. A solid ball of iron the size of Pluto, as hot as the surface of the sun, kept solid by being crushed under 3 million atmospheres of pressure. An ocean of liquid metal larger than the moon, freezing slowly from the inside, churning and twisting with the spin of the planet, generating 1 billion amperes of current, and a magnet that makes itself. And a magnetic field so weak that a fridge magnet outdoes it up close, yet so vast that it shields the entire planet from the sun. All of it real, all of it deduced from a distance, from a world we have never touched, by listening to earthquakes and reading meteorites and crushing tiny specks of iron in laboratories to mimic the pressures of the deep.
And here is the heart of how I want us to think about all of this tonight, because there is a way this story is usually told, and it is the wrong way, and we are not going to tell it that way. The usual way is fear. You may have heard it. The magnetic field is weakening, they say. The poles are about to flip. We are overdue for a catastrophe. The shield is failing and disaster is coming. It is a story built to frighten, and it is, quite simply, not true, not in the way it is told.
The honest science is calmer, older, and far more wonderful than the scare. Because what we are looking at when we look at the geodynamo is not a doom clock counting down. It is a living engine. A machine that has been running, by the best evidence we have, for at least 3.5 billion years. Through ice ages and warm ages, through the rise and fall of whole forms of life, through the breaking apart of continents and the opening and closing of oceans, this engine has turned and turned and kept turning. It has shifted and stuttered and changed countless times. it has weakened and recovered. It has, as we will see in the hours ahead, even flipped its poles entirely, north becoming south and south becoming north. And it has done that not once but hundreds of times, and life carried on each time, and the sky stayed blue, and the air stayed put. This is not a story of a machine about to die. It is the story of a machine that is alive, breathing, shifting, the way a living thing breathes and shifts, and every dramatic thing it does, every flicker and wander and weakening, is not a warning of the end, but a sign of the engine working, exactly as it has always worked, exactly as it will go on working long after every one of us is asleep for good. There is a hole in the shield right now over the South Atlantic, and we will visit it, and I will show you how the most powerful telescope ever built closes its eyes every time it passes over that hole. There is a place where the magnetic North Pole is racing away across the top of the world, faster every year, and we will follow it. There was a night 42,000 years ago when the shield almost failed, when it fell to a tiny fraction of its strength, and some scientists believe that near collapse changed who survived on this planet. We will go there too. But none of it is doom. All of it is the engine, breathing. And there is a way to feel the stakes of this engine without any fear at all, and it is to look up, or rather to look across, at our neighbor. Because Mars, the red planet, the desert next door, once had an engine just like ours. Mars, billions of years ago, had a spinning iron core generating its own magnetic shield, and beneath that shield it may well have had thicker air and running water and the possibility of something more. And then around 4 billion years ago, the engine of Mars stopped. The core cooled, the dynamo died, the shield switched off. And without the shield, the sun went to work, stripping the air away into space, little by little, over the long ages. And here is the part that should make you grateful for the iron turning beneath your bed. Mars is still bleeding. To this very day, the air of Mars is leaking away into the dark, escaping into space at a measurable rate, and we will look at exactly how we measure it. Mars is the answer to the question of what happens when the engine stops. It is not a guess. It is a real planet, a dead, cold, slowly suffocating planet, drifting through the same sunlight that falls on us. And the only difference between its fate and ours is that our engine is still running, and its engine fell silent 4 billion years ago. So that is the journey, and that is the spirit of it. We are going to go down, all the way down, to the spinning iron engine at the center of the Earth. We are going to learn how a planet builds a magnet out of molten metal, and we are going to learn how, against all reason anyone knows, we are going to follow the shield up into space and watch it turn aside the wind from the sun. We are going to read the frozen record of all the times the engine has flipped, hocked into ancient lava and into stripes upon the floor of the sea. And at the end of it all, we will come back up, and you will know in a quiet and reassured way that the trembling and shifting of the field is not the end of anything, but simply the sound of a living world keeping itself alive. For now, though, let us stay here a moment longer, in the deep, with the solid heart and the churning sea. Let yourself feel the strangeness of where you are. You are lying on a thin skin of cooled rock, the merest film over the body of the planet. Below that skin is the mantle, hundreds upon hundreds of kilometers of hot, slow-flowing rock. And below the mantle, 2,890 kilometers down, the rock gives way at last to metal, to the great ocean of liquid iron, turning in the dark, casting up its invisible shield. And at the center of that ocean, the solid heart, the Pluto-sized ball, glowing at the temperature of the surface of the sun, held still by the weight of the world, freezing slowly, atom by atom, age by age. It has been doing this for billions of years. It was doing it before there were any eyes to wonder at it. It was doing it when the first single cells drifted in the early seas, and when the first fish crawled onto land, and when the great reptiles walked, and when the ice came and went, and when the first human beings looked up at the auroras in the polar sky without the faintest idea that the green light dancing above them was the visible signature of that hidden engine, working, as it always works, far beneath their feet. And it is doing it now, this very second, as you lie here, as your breathing begins to slow, as the day's weight begins to lift from you. The iron is turning, the shield is holding, the sky is blue and the air is here, and the world is alive, because at the center of everything, a frozen heart the size of Pluto sits crushed and patient in the dark, and an ocean of molten metal turns slowly around it, and from that turning comes the quiet field that wraps us all. We have only just begun the descent. There is so much more to come, and we will take every step of it slowly, with no hurry at all. But first, we must answer the question I left open, the one that should be turning gently in your mind even now. We have never seen the core, we have never touched it, we have never come within thousands of kilometers of it. So how, truly, do we know it is there at all? How did anyone first hear the heart of the earth? For that we must go back to the trembling of the ground, to the great earthquakes of the past century, and to the quiet listeners who learned to read the echoes passing through the body of the planet, and to a woman in Copenhagen who, by following those echoes with extraordinary care, found the solid heart that no one had ever seen. The story of how we know anything about the core at all begins not with a telescope or a drill or a laboratory, but with catastrophe. It begins with the earth shaking. When the ground moves, it moves in waves, not in the loose, casual sense of a metaphor, but in a precise and literal physical sense. Energy released by a rupture deep in the crust radiates outward through the rock in the form of seismic waves, and those waves travel through the body of the planet the way sound travels through water, or the way a vibration passes along a stretched string from one hand to the other. They move through solid rock differently than they move through liquid. They bend when the material around them changes. They reflect at boundaries. They leave shadows where they cannot pass at all. And if you place sensitive instruments on the surface of the earth and listen, patiently, carefully, recording the faint arrivals of waves that have just traveled thousands of kilometers through solid and liquid rock, you can read in those arrivals the interior structure of a planet you will never visit. This is seismology, and it is, in its way, as remarkable as any discovery ever made, because it means that the Earth reveals its innermost architecture every time it shakes. Every great earthquake is also a probe, a signal sent involuntarily through the body of the planet, and the seismograph stations distributed across the surface are the listening posts that decode it. The first man to realize that this decoding was possible in any formal and scientific sense was a British geologist named Richard Oldham. In 1906, Oldham published an analysis of seismic records from the great earthquakes of the previous years, and noticed something that had been sitting, unread, in the data for some time. Seismic waves come in more than one kind. There are the primary waves, the P waves, which are compressional. They push and pull the material they travel through in the same direction they are moving, the way sound pushes and pulls air. And there are the secondary waves, the S waves, which are shear waves. They move the material sideways, perpendicular to their direction of travel, the way a rope ripples when you shake one end of it. P waves can travel through anything: solid rock, liquid iron, a fluid of any kind. S waves cannot travel through a liquid at all, A liquid has no rigidity, no resistance to being sheared sideways, and so a shear wave entering a liquid simply dies, its energy absorbed without transmission. Oldham noticed that on the far side of the Earth, from a large earthquake, in the zone that should have received both kinds of waves, the S waves were missing. They arrived where they should have arrived over distances up to a certain point, and then beyond that point they were simply absent. There was a shadow zone, a region of the Earth's surface where no S waves came through from a large distant earthquake, and the only explanation for a shadow was that something inside the Earth was blocking them. Something liquid. Something that shear waves could not cross. That something was the outer core. Oldham's 1906 paper was the first to formally identify the core as a distinct region of the Earth's interior, and to recognize that it must be, at least in part, liquid. 7 years later, in 1913, a German geophysicist named Benno Gutenberg refined the picture considerably. Working with more data, more stations, more careful analysis, Gutenberg was able to calculate where the boundary between the rocky mantle and the liquid core actually sat. He placed it at approximately 2,900 kilometers below the surface, a figure that has since been refined to about 2,090 kilometers. It is called the core mantle boundary, and Gutenberg placed it with extraordinary accuracy for a man who had never been within a fraction of that depth of the thing he was measuring. The boundary still carries his name in the literature, and it should, because it was an act of extraordinary geometric reasoning carried out entirely in the abstract, from tremors recorded on paper. But Oldham and Gutenberg had identified only the existence and location of the outer core. They had established that something liquid was down there. What was inside that liquid was still unknown, because any seismic wave that could penetrate the outer core at all, the P waves, should, on the other side, tell them something about what was waiting deeper still. And for a time, the assumption was that the P waves simply converged toward the center and told a consistent story, a liquid all the way through. Then came Inge Lehmann. Lehmann was a Danish seismologist born in 1888 who spent decades working in Copenhagen analyzing seismic records with meticulous, almost obsessive precision. In 1936, she published a paper that was extraordinary in its brevity and its consequence. Working through the records of large earthquakes, she noticed that P waves were arriving in places where they should not have been able to arrive, in the deep shadow zones on the far side of the planet, showing up faint but real, where theory said they should be absent, or at most vanishingly weak. The only way to explain those anomalous arrivals was if something at the very center of the Earth was reflecting and refracting the waves in an unexpected way. Something with different properties, something that was not simply more liquid. Inge Lehmann proposed, on the basis of those faint and ghostly arrivals alone, that there was a solid inner core inside the liquid outer one, a solid sphere deep in the heart of the liquid, whose boundary reflected P waves in ways that the surrounding liquid could not. Her paper was 2 pages long. Her conclusion was correct. The inner core exists. She found it the way a blind person finds a wall, by listening for what comes back. The inner core was confirmed and refined over the following decades as seismographic networks improved and more earthquake records accumulated. It sits inside the liquid outer core, beginning at about 5,550 kilometers depth and extending to the center of the Earth at about 6,371 kilometers. Its radius is approximately 1,020 kilometers, which, as was noted earlier in our descent, is slightly larger than the radius of the dwarf planet Pluto. And it is solid, entirely, genuinely, counterintuitively solid, despite temperatures there that approach 5,400 degrees Celsius, temperatures comparable to the visible surface of the Sun. The fact that it is solid at such temperatures is itself a consequence of the pressure bearing down upon it. At Earth's center, pressure reaches approximately 360 gigapascals, more than 3 million times the atmospheric pressure you feel on your skin as you lie here. Under that kind of compression, iron's melting point rises dramatically. The atoms of the metal are forced so close together, held under such immense confinement, that they cannot flow into the disordered arrangement of a liquid, even at temperatures that would vaporize most metals at the surface. The pressure wins. The iron stays solid. The inner core is the paradox at the center of everything, as hot as the sun, as dense as anything in the geological world, and yet frozen in place. But we have never touched it. We have never seen it directly. And this is the truth of everything we know about the core. It is all inference. It is all reading the echoes. There are exactly two natural windows into the interior of the Earth, and both of them are indirect. The first is seismology, earthquakes as involuntary probes, which we have just traced from Oldham through Gutenberg to Lehmann. The second is the sky in the form of meteorites. Iron meteorites, the dark, heavy metallic chunks that occasionally fall through the atmosphere and are found lying in deserts and fields and polar ice, are not rocks in any conventional sense. They are fragments of other worlds. They are pieces of asteroids that formed in the early solar system, grew large enough to differentiate by density just as Earth did, and then collided and broke apart. When they broke, they exposed their cores, and those cores, those ancient shattered hearts of small dead worlds, drifted through space until they fell here. We can hold them. We can cut them open. We can analyze their chemistry and their crystal structure and their isotopic ratios. And what they show us, dense iron-nickel alloy studded with inclusions of lighter elements bearing the crystal textures of metal that cooled very slowly under great pressure, is our best physical analog for what sits at the center of the Earth. The Widmann-Stetten pattern visible in sliced iron meteorites, those long, interlocking bands of iron-nickel crystals that are unmistakable and unlike anything formed at the surface, takes millions of years to form. It requires slow cooling under pressure. It is a record of an interior slow and deep and old, and it is there in a piece of metal you can hold in your hand. Beyond meteorites, there is a third window, more technical but deeply important, the diamond anvil cell. This is a laboratory device of remarkable ingenuity in which two gem-quality diamonds, facets pressed together, squeeze a tiny sample of material between their tips to pressures that rival those in Earth's deep interior. The sample is heated simultaneously with laser beams and then examined with X-rays to determine its crystal structure, its density, its behavior. Scientists have used diamond anvil cells to study how iron-nickel alloys behave at core conditions, how they melt, how they solidify, what crystal forms they take, how light elements dissolve into them. The results of those experiments inform every model of what the core actually is. But none of this, not the seismic waves, not the meteorites, not the diamond anvil cells, has brought a single human being within 3,000 kilometers of the core. The deepest borehole ever drilled into the Earth was the Kola superdeep borehole in the Kola Peninsula of northwestern Russia, begun in 1970 and drilled over many years of extraordinary technical effort to a depth of 12.26 kilometers, 12 kilometers and a few hundred meters. The distance from the surface to the center of the Earth is 6,871 kilometers. The Kola superdeep reached less than 1/200th of the way there. And at that depth, the heat alone, temperatures that reached around 180 degrees Celsius, far hotter than models had predicted, stopped the drilling. The rock had become plastic and hot and difficult beyond the capacity of the available equipment, and the project was abandoned in 1992. 12 kilometers out of 6,371. We scratched the surface. Everything we know about what lies below comes from listening, from falling metal, from laboratory mimicry. And yet it is enough. The seismic record is now so extensive, the network of listening stations so dense, the mathematical tools so refined, that the overall picture of the Earth's interior is genuinely robust. The outer core is there. It is liquid. It is predominantly iron, alloyed with some nickel and a small percentage of lighter elements. Sulfur, oxygen, silicon, possibly carbon, and hydrogen. The exact mix still debated, still being refined in laboratories around the world, but the broad character known. The inner core is solid iron nickel, distinct and real, found by a woman in Copenhagen reading arrivals on paper strips in 1936. And between them and all around the inner core is the vast ocean of liquid metal that makes the machine run. Now let us talk about the machine itself. The outer core is a shell of liquid iron-nickel alloy, roughly 2,200 kilometers thick. To hold that number gently for a moment, 2,200 kilometers. The distance from London to Warsaw is about 1,500 kilometers. The distance from New York to Denver is about 2,600 kilometers. The outer core, this churning ocean of liquid metal, is a shell whose thickness compares to the width of a continent. It surrounds the solid inner core entirely, and it is itself surrounded entirely by the rocky mantle above. It is locked in, encased, a sea with no coast and no sky, only rock above and a frozen metal heart below. This liquid iron is electrically conducting, not in the casual sense that it can carry a trickle of current. Iron at core conditions, under enormous pressure and at enormous temperature, is an extremely good electrical conductor. It behaves in this sense more like copper wire than like rock. And the motion of electrically conducting fluid has a property that is the root of everything. When conducting fluid moves in the presence of even a weak magnetic field, the motion of the charges within the fluid generates electric currents, and those electric currents themselves produce magnetic fields. The fluid is not just moving through the field. The fluid is a field generator in its own right. This is the principle behind every electric generator ever built. In the generators that produce the electricity running through your walls right now, copper coils spin inside magnetic fields, and the motion of electrons in the copper wire produces current. The geodynamo runs on the same physics, but with a liquid iron ocean instead of copper wire, and with Earth's rotation providing the organized motion, and with no external magnetic field needed to start the process once it is already going, because the field produced by the current can maintain and amplify itself in a self-exciting loop. Three things are required for a dynamo to work: a large volume of electrically conducting fluid, an energy source to keep that fluid in motion, and rotation to organize the motion into forms that sustain rather than cancel the magnetic field. Earth has all three and has had them for a very long time. The energy source is twofold and the two parts are distinct. The first is thermal. The core is still hot from its formation, and it has been losing heat slowly into the mantle above for billions of years. Heat flowing out of the core heats the bottom of the mantle and, within the core itself, creates the conditions for thermal convection. Hot material rising, cooler material sinking, just the way hot air rises from a radiator and the cool air of a room sinks to replace it. This thermal convection stirs the liquid iron. It was, in the earlier history of the Earth, probably the dominant power source for the engine. But there is a second energy source, subtler, and perhaps now more important: compositional convection. The Earth has been cooling for 4.5 billion years, and as it has cooled, the solid inner core has very, very slowly been growing. Iron freezes onto its outer surface, crystallizing out of the surrounding liquid, adding another layer, expanding the solid ball by a fraction at rates so slow they are almost incomprehensible on any human timescale. This freezing, this gentle, continuous solidification has two consequences that drive the engine. First, it releases heat, the latent heat of crystallization, the energy given off whenever a liquid becomes a solid. That heat warms the surrounding liquid and contributes to thermal convection. But second, and crucially, it expels impurities. Pure iron crystallizes preferentially. The lighter elements mixed into the liquid iron, the sulfur, the oxygen, the silicon, are excluded from the growing solid and remain in the liquid. They accumulate at the inner core boundary, a thin zone of liquid slightly enriched in these lighter, less dense elements. And lighter means more buoyant. Those lighter dregs of the crystallization process rise upward through the surrounding liquid iron like bubbles of oil rising through water, carrying their buoyancy upward and driving a convection that is not thermal but compositional. A stirring powered not by heat but by the chemistry of freezing iron. This is why the inner core is sometimes described as the fuel pump of the engine. Not because the solid itself does anything, it simply sits there, frozen in the dark, growing by fractions. But the act of its growing drives the ocean of metal around it into motion. Every atom of iron that locks into the solid surface of the inner core releases a pulse of buoyancy into the liquid above. Over billions of years, those pulses have maintained a churning that nothing else could sustain with the same consistency. The motion driven by these two forces, thermal and compositional, would, on its own, be chaotic and largely random, the swirling of a vast, dark, unstructured fluid. But it is not unstructured, it is organized. And the organizer is Earth's rotation. The Coriolis effect is one of the more unintuitive features of physics, but it is real and measurable at every scale, from ocean currents to storm systems. It arises from the fact that Earth is rotating, and that anything moving freely on or inside a rotating sphere is deflected by that rotation. In the northern hemisphere, large-scale fluid motions tend to be deflected to the right. In the southern hemisphere, to the left. You see it in the way hurricanes spiral, in the way wind systems organize themselves. In the outer core, the Coriolis effect has a specific and powerful consequence for the convecting liquid iron. It organizes the rising columns of buoyant fluid not into random blobs or sheets, but into rotation-aligned structures, columns that tend to orient themselves parallel to the Earth's spin axis. These are sometimes called Taylor columns, after the mathematician Geoffrey Taylor, who first described theoretically how rotation imposes this kind of organization on fluid flow in a rotating system. Think of them not as rigid cylinders, but as organized helical currents, streams of liquid iron rotating as they rise, spiraling in a coherent way, all aligned broadly with the same axis. The direction is imposed not by any property of the iron itself, but by the rotation of the whole planet around them. It is this organized helical motion of conducting fluid that makes the dynamo work. The principle is that random, chaotic stirring of a conducting fluid in a magnetic field would tend to generate currents that cancel each other out, that produce and destroy magnetic fields in equal measure without building a net result. But helical motion, organized, rotation-aligned, coherent, generates currents that reinforce each other. It is the difference between the random shuffling of a deck of cards and a systematic sorting. The rotation sorts the flow. The sorted flow generates coherent currents. The coherent currents produce a net magnetic field. And then something remarkable happens, which is the heart of the self-exciting loop. The magnetic field produced by those currents acts on the moving conducting fluid, because moving conducting fluid in a magnetic field experiences forces, and those forces can alter the flow. Under the right conditions, the field and the flow reach a kind of dynamic balance. The flow sustains the field organizes the flow, and neither can exist without the other. The system becomes self-maintaining. It is not powered by the magnetic field. The energy comes from the heat and the chemical buoyancy, as we described. But the field does not need an external magnet to exist. Once it is established, it sustains itself from the energy of the convection alone, the way a spinning flywheel keeps spinning long after the initial push, as long as there is something to keep it turning. This self-sustaining quality is what physicists mean when they call it a self-exciting dynamo, and it is what separates a geodynamo from a simple electromagnet. A simple electromagnet requires an external power supply to maintain the current in its coils. The geodynamo requires only continued convection in the outer core, and convection will continue as long as the Earth keeps cooling, which it will do for billions of years yet. The electric current flowing through the outer core is, on any human scale, staggering. The total current circulating in the outer core is estimated on the order of 1 billion amperes. 1 billion. For comparison, a large household circuit breaker typically protects against currents of 15 or 20 amperes. 1 billion amperes is a current scale that has no meaningful analog in the technology of the surface world. And yet it flows silently, invisibly, thousands of kilometers beneath your feet, and has been flowing for billions of years. The result of all this organized, current-carrying, rotating fluid motion is a magnetic field. And the dominant structure of that field, at Earth's surface and beyond, is a dipole, a configuration with one north pole and one south pole, shaped broadly like the field around a bar magnet. This is not the only possible outcome of a dynamo. In principle, a rotating conducting fluid could generate a field with many poles, or a field of complex and chaotic topology. The reason Earth's field is predominantly dipolar is that the dipole configuration is stable and energetically favored in the kinds of large-scale rotation-dominated convection that occurs in the outer core. The Taylor columns and their organized helical flows preferentially generate a dipole. The more complex multipolar components of the field exist. They are real and measurable, but they are weaker and change faster, while the dipole persists. The axis of this dipole is not perfectly aligned with Earth's rotation axis. It is tilted at present by about 11 degrees. The geographic North Pole, which marks the point where Earth's rotation axis meets the surface, and the magnetic North Pole, where the dipole axis meets the surface in the north, are not the same place. They are separated by several hundred kilometers, and the angular difference between geographic north and magnetic north, the direction a compass needle points versus true north, is called magnetic declination. Every navigation chart ever printed for use with a compass has carried a correction for magnetic declination because the two norths are not the same. And the magnetic North Pole moves, as we will come to understand more fully in time, while the geographic North Pole stays fixed. But here, at this moment in the descent, we must pause on something that is genuinely counterintuitive, something that is rarely explained clearly even when the geodynamo is discussed. The magnetic North Pole, the place on Earth's surface toward which the north-seeking end of every compass needle points, is, in the language of physics, not actually a north magnetic pole at all. A north magnetic pole, by definition, is where magnetic field lines emerge from the Earth and go out into space. A south magnetic pole is where they re-enter. Field lines run from north to south. They loop from one pole to the other, emerging at one and returning at the other. And the north end of a compass needle is attracted to and points toward what we call the magnetic North Pole. But attraction in magnetism works oppositely to attraction in names. Opposite poles attract. The north end of a compass needle is attracted to a south magnetic pole, not a north one, which means the thing we call the magnetic North Pole, the place up in the high Arctic toward which all compasses gesture, is, in strict magnetic terminology, a south pole. Field lines there are flowing into the Earth, not out of it. The geographical accident of naming it north, based on direction, rather than on its physics, has persisted for centuries. The actual magnetic South Pole in the strict physical sense sits in the northern hemisphere. The actual magnetic North Pole in the strict physical sense is in Antarctica. We have been living with the compass pointing what is technically the wrong direction for the entire history of navigation. It works, of course. A map is just a convention, and as long as everyone agrees that the thing the compass points toward is called north, there is no practical problem. But the underlying physical reality is quietly reversed. The arrow on your compass that says N is pointing toward a place the physics would call S. And that place, wherever exactly it sits tonight, is moving. It has been moving for as long as we have been able to track it, but the pace of that movement has not been constant, and in recent decades it has become something closer to a sprint. Through much of the 20th century, the magnetic North Pole drifted slowly across the Canadian Arctic. A few kilometers a year, the kind of drift that is easy to absorb, easy to correct for in charts and navigation systems. Then sometime around the turn of the millennium, it accelerated. By the 2010s, it was covering 40, 50, sometimes 60 kilometers in a single year. It had crossed the international date line. It was moving out of Canadian territory and racing toward Siberia, toward Russia, toward a position that would have been geographically unimaginable to any navigator of the last several centuries. The speed of this drift became consequential enough that the world magnetic model, the mathematical description of the field used by smartphones, aircraft, ships, and military systems to convert a compass reading into a true bearing, had to be updated ahead of its usual schedule. The 2019 update was released early because the pole had drifted so far from the model's predictions that navigational errors were beginning to accumulate in sensitive applications. The phone in your pocket, when it tells you which way to walk, is drawing on a continuously revised approximation of a field that has not sat still for a single day of Earth's existence. And yet all of this, the tilt, the drift, the naming paradox, the wandering pole, is merely the surface expression of something happening thousands of kilometers beneath the ground you are lying on. To understand why the pole moves, why the field is tilted at all, why there is a magnetic field surrounding this planet in the first place, you have to go somewhere no human instrument has ever reached and ask how we came to know anything about it. The answer begins not with a drill or a camera, but with an earthquake. When the ground shakes, it sends waves outward in all directions, through rock, through liquid, through the entire body of the planet. These are seismic waves, and they travel at speeds that depend on the density and state of whatever material they are passing through. Some of them, the ones called P waves or pressure waves, can travel through both solid and liquid. Others, the ones called S waves or shear waves, can only travel through solid material. They require the medium to flex and spring back sideways, the way a rope flexes when you snap it. Liquid does not do this. Liquid flows rather than springs, and so S waves moving outward from an earthquake simply stop at the boundary where solid rock gives way to liquid iron. They go no further. This silence on the far side of the planet, the zone where S waves should have arrived but did not, was what allowed Richard Oldham, a British geologist studying earthquake records in 1906, to conclude that Earth had a large liquid interior. He could not see it, no one could, but the absence of a wave on the other side of the world was itself a kind of evidence, a shadow cast by something that would not let the wave through. He measured where the shadow fell and worked backward to the shape and position of whatever was casting it. The result was a liquid core, roughly deduced from the geometry of missing signals. Benno Gutenberg, a German seismologist working a few years later, refined this dramatically. By 1913, he had worked out from the careful analysis of wave arrival times at stations around the world that the boundary between the solid rocky mantle and the liquid core sits at approximately 2,890 kilometers below the surface. The core mantle boundary, a number derived entirely from listening to how earthquakes echo through a planet no one has ever opened. Gutenberg's estimate, reached with the instruments and techniques of his era, has held up with remarkable fidelity against everything seismology has done since. The value we use today is close enough to his that the difference is a rounding matter. But Gutenberg's discovery was still a liquid core, undifferentiated, one enormous ocean of molten iron from that boundary all the way to the center. It took another person working another 2 decades later to find that the center is not liquid at all. Inge Lehmann was a Danish seismologist, and in 1936 she published a paper whose entire argument was contained almost entirely in its title, P. The paper was a study of P waves, the waves that can travel through liquid, and what happened to them when they reached the depths of the core. Lehmann noticed something that others had recorded but not explained. Some P waves that should have been deflected away by the liquid interior were instead arriving at the other side of the planet at angles that suggested they had been bent, refracted, by something denser at the very center. Something solid, something that bent the waves back outward in a way that only a distinct, harder material could. Her conclusion, offered carefully and without fanfare, was that inside the liquid outer core there sits a solid inner core. A ball of iron compressed by so much weight from above that despite temperatures comparable to the surface of the sun, it cannot flow. It has been squeezed into stillness by the sheer mass of everything pressing down on it. She was right, and she worked it out from the slight mistiming of waves at seismograph stations scattered across a world that had no idea it had a solid heart. So we have our picture now, built entirely from inference and mathematics and the careful listening to a planet that shakes, a solid inner core, roughly 1,220 kilometers in radius, surrounded by an outer core of liquid iron-nickel alloy approximately 2,200 kilometers thick, all of it beginning nearly 3,000 kilometers down and extending to roughly 5,150 kilometers depth, where the solid rock of the lower mantle resumes. The outer core alone is a volume of conducting fluid far larger than the Moon. It has never been touched. The deepest hole ever drilled by human hands, the Kola super-deep borehole in Russia, reached 12.26 kilometers before the project was abandoned, a distance that represents, in proportion to the journey to the center, something close to nothing. The core might as well be on another planet. And yet we know its composition approximately because we have a second window that has nothing to do with earthquakes. Iron meteorites, chunks of metal that fell to Earth from the shattered cores of ancient planetesimals, small rocky bodies that formed in the early solar system and were later broken apart by collisions, give us a sample of what the interior of a rocky, differentiated world looks like. They are iron-nickel alloys, dense and heavy, crystallized in patterns called Widmanstetten figures that form only over millions of years of slow cooling under conditions that could not exist on a surface. They are, in a sense, the exposed hearts of dead worlds. And they resemble in their broad chemistry what we calculate Earth's core to be, not identical. Earth's core contains a few percent of lighter elements, sulfur or oxygen or silicon or some combination of these, because the core is measurably less dense than pure iron-nickel would be at those pressures, but close enough that the meteorites function as analogues, as physical evidence you can hold in your hand for something you will never otherwise touch. The third window is even more extreme. In a diamond anvil cell, a laboratory instrument that uses 2 tiny cut diamonds as opposing jaws, scientists can squeeze small samples of material to pressures that rival those at Earth's center. 360 gigapascals, more than 3 million times the pressure of the atmosphere at sea level, and then heat them with lasers to core-level temperatures. They watch iron melt and refreeze, They measure how it conducts electricity at those pressures, how its crystal structure changes, how light passes through it. They map, in a volume smaller than a grain of rice, the physics of a place 4,000 miles beneath them, and the results inform and confirm the seismic models, filling in details the waves alone cannot provide. From these three sources, seismology, meteorites, and the diamond anvil cell, we have built a picture confident enough to explain the magnetic field, its behavior, its age, and its occasional instability. And the explanation is the geodynamo. The principle is not complicated to state, though the mathematics of it has occupied some of the best geophysicists of the last century. Moving electrically conducting fluid in a pre-existing magnetic field generates electric currents. Those electric currents generate their own magnetic field. If the geometry and the motion are right, the new magnetic field reinforces the original one. The original field then acts on the moving fluid, and the fluid moves more, and the current grows, and the field strengthens again. The loop is self-sustaining. There is no external battery, no source of magnetism that has to be replenished from outside. Given the right ingredients, the system powers itself. Earth has all three of those ingredients. It has a vast volume of electrically conducting fluid, the liquid outer core, iron-nickel, which conducts electricity readily. It has energy to drive convection, heat escaping from the core into the mantle above, and, crucially, something else. As the planet slowly cools over geological time, iron at the surface of the inner core crystallizes and freezes onto it. The inner core is growing very slowly, adding to itself as the heat of formation dissipates outward, and as iron freezes, the lighter elements mixed into the liquid, the sulfur, the oxygen, the silicon are expelled. They are less dense than the surrounding iron, and so they rise. This is compositional convection, also called chemical convection, and it stirs the outer core from the bottom upward in a way that may be even more powerful than the thermal convection driven by heat alone. The inner core is not a passive occupant of the center. It is the engine's fuel pump, continuously expelling buoyant material that rises and drives circulation through the whole vast ocean of liquid metal above it. The third ingredient is rotation. Earth spins once every 24 hours, and the Coriolis effect, the deflection that makes hurricanes spiral, that bends the path of anything moving across a rotating sphere, organizes the rising and falling currents of liquid iron into coherent rotating columns. These are called Taylor columns, and they align with the rotation axis. The circulation is not random. It is structured, shaped by the spin into something that can sustain a large-scale organized magnetic field rather than a chaotic tangle of small competing fields that cancel each other out. The result is a magnetic dipole, a field that, to a first approximation, looks like the field of a giant bar magnet buried along the spin axis, with one pole in the north and one in the south. Not exactly along the spin axis, the geomagnetic axis is tilted about 11 degrees away from the geographic rotation axis, which is why magnetic north and true north differ, why every map and chart carries a small correction for magnetic declination, and why the two poles wander independently of each other. But roughly dipolar, roughly organized and carrying through the crust and up into space a field that at Earth's surface averages somewhere between 25 and 65 microtesla, depending on where you are standing. That is a very weak field by the standards of laboratory magnets. The magnet holding a note to your refrigerator door is likely stronger in terms of field strength at its surface. But strength at a surface is not the point. The geodynamo's field fills space. It extends outward from the planet in all directions, shaping a vast invisible structure hundreds of thousands of kilometers across, and the total electrical current required to sustain it, circulating through the outer core at this moment while you lie still and the planet turns, runs on the order of 1 billion amperes. And that field, Thin as a whisper at any single point, yet enormous in its reach, is the thing standing between every living creature on this planet and the full violence of the sun. To understand what the geodynamo has built around us, you have to leave the Earth entirely, at least in imagination, and look at it from outside. Picture the planet suspended in space, and around it, invisible but real, a vast asymmetrical bubble. Not round, not neat. The solar side of this bubble is compressed, pushed inward by constant pressure. The side facing away from the sun is drawn out into a long, trailing tail, the way a teardrop stretches and elongates when it falls through air. This is the magnetosphere, the magnetic envelope of the Earth, and it is not a fixed or permanent structure. It breathes, it flexes, it shivers in response to every gust and surge from the star at the center of the solar system. The sun is not quiet. Even on calm days in the spaces between flares and eruptions, the sun releases a continuous outward stream of charged particles, protons and electrons moving at extraordinary speed, roughly 400 kilometers per second on average and sometimes faster, up to perhaps 800 kilometers per second in the more intense fast streams. This is the solar wind, and it has been blowing outward from the sun since the solar system formed, filling the space between planets with a constant pressure of moving charged matter. If you could see it, it would look nothing like wind. There is no turbulence you could watch, no dust being blown, no leaves lifting from the ground. It is radiation. It is a ceaseless, invisible current, striking everything in the solar system that lacks a strong enough magnetic shield to deflect it. Earth has the shield, and the first sign of the shield, if you could travel outward from Earth toward the sun, would be the bow shock. The bow shock forms because the solar wind moves supersonically, faster than the speed at which information can propagate through that thin plasma. When it encounters the magnetic field of the Earth, it cannot slow down gradually. It stops abruptly, piling up in a standing wave of compressed, heated plasma. The bow shock sits roughly 90,000 kilometers upstream from the Earth on the day side, which is roughly 13 to 15 Earth radii out into space. This is where the solar wind first encounters the Earth's field. This is where the outer boundary of our shield catches the first blow. Beyond the bow shock, closer to the Earth, is the magnetopause, the actual surface of the magnetosphere, the boundary where the magnetic pressure of the Earth's field balances the dynamic pressure of the solar wind. The precise location of the magnetopause shifts with the strength of the solar wind. When the sun is active and the wind is blowing hard, the magnetopause is pushed closer in. When the wind quiets, it expands outward again. The magnetosphere breathes with the sun's mood. On the day side, that compression means the field is squeezed. On the night side, the story is entirely different. The solar wind sweeps the field back and out, drawing it into a long magnetotail that extends for hundreds of thousands of kilometers behind the planet in the direction away from the sun. The magnetotail stretches past the orbit of the moon. On some estimates, it extends perhaps 1 million kilometers behind us, thinning and eventually merging with the general interplanetary field. A vast invisible wake trailing in the darkness, the elongated downstream shadow of the shield. Within this bubble, within the volume of space carved out and maintained by the geodynamo's field, the charged particles of the solar wind cannot easily penetrate. Most of them flow around the magnetosphere the way water flows around a stone in a stream, diverted, carried off downstream, never reaching the surface. And it is this diversion, this simple, physical, the magnetic force turning a charged particle away from its original path, that has made complex life possible on this planet. But the shield is not perfectly sealed. Some particles get in, particularly at the poles where the field lines converge and dip down toward the surface, and particularly during geomagnetic storms when the sun throws a particularly intense burst. and the magnetopause is briefly disrupted, and some of the particles that enter the magnetosphere get trapped rather than deflected. They follow the curving field lines back and forth between the poles, bouncing in great arcing trajectories through a region of space above the equator, caught in a magnetic bottle of their own trapping. This is where two of the most important discoveries of the early space age were made in those first years after Sputnik, when human instruments first flew above the atmosphere and into the near-space environment. In 1958, an instrument aboard Explorer 1, the first successful American satellite, detected something unexpected. The radiation counts, which should have risen steadily with altitude, went high and then suddenly dropped, not because there was less radiation, but because the detector was saturated, overwhelmed. James Van Allen, the physicist who had designed the instrument and who had argued for putting radiation detectors on the satellite in the first place, understood what was happening. The satellite was flying through zones of concentrated trapped radiation so intense that the instruments couldn't keep up. There were regions of space around the Earth where the magnetic field had gathered charged particles into two great donut-shaped belts, one closer in and one farther out, both centered on the equatorial plane and both presenting a significant radiation hazard to anything passing through them. These are the Van Allen radiation belts, named for the scientist who recognized them in that early data, and their discovery was the first major scientific revelation of the space age. Before Explorer 1, no one had known they existed. The field had been keeping its secrets. The inner Van Allen belt sits roughly between about 1,000 and around 12,000 kilometers altitude, and it is dominated by high-energy protons, some of them produced when cosmic rays strike atoms in the upper atmosphere and send secondary particles spiraling into the trapping region. The outer belt extends from roughly 13,000 to perhaps 60,000 kilometers altitude and is filled mainly with high-energy electrons, a population that swells dramatically during geomagnetic storms when the Sun sends a burst of particles that gets swept into the belts. Both belts are hazardous to spacecraft electronics, which is one reason the orbits chosen for satellites are carefully designed either to stay below, or to stay above, or to pass through the belts as quickly as possible on the way out. And between these belts, occupying the orbital altitudes where the field is somewhat quieter, is where most of our critical infrastructure in space now lives and works. The auroras are the shield made visible. When charged particles do make it down along the field lines toward the poles, whether they are particles that sneaked through the magnetopause or particles from the outer Van Allen belt that have been disturbed into a new trajectory, or particles guided in through the polar cusps where the field geometry allows closer access, they travel down into the upper atmosphere where the air is thin but present. There they collide with atoms of oxygen and nitrogen, exciting those atoms to higher energy states, and as the atoms relax back down, they release that energy as light. Oxygen produces the most familiar aurora colors, a vivid green at around 100 kilometers altitude, a rarer deep red at higher altitudes. Nitrogen contributes purples and blues. The exact colors depend on which atoms are present and how energetic the collision was. You have perhaps seen photographs of the aurora borealis arching across a night sky over Scandinavia or Iceland or Canada. Great curtains of light moving and shifting and rippling as the particle flow changes moment by moment. Or the southern equivalent, the aurora australis, visible from the tip of South America or the Antarctic. What you are looking at in those photographs is the geodynamo announcing itself. You are watching the top of the atmosphere glow because the magnetic field has guided charged particles down to precisely those points, the polar regions, where the field lines converge and enter the Earth. The auroras trace the shape of the field. They mark the places where the shield allows passage, funneling energy harmlessly into light rather than letting it scatter where it could cause more disruption. There is a clarification worth making here, quietly and without fanfare, because this particular confusion appears often even in thoughtful discussions of the topic. The magnetic shield and the ozone layer are not the same thing, and they protect against different things. The ozone layer, that thin band of ozone molecules in the stratosphere, roughly 15 to 35 kilometers above the surface, is a chemical shield against a particular form of radiation, ultraviolet light, which is uncharged electromagnetic radiation that travels at the speed of light, cannot be deflected by a magnetic field at all. The magnetosphere offers no protection whatsoever against ultraviolet, and the ozone layer offers no protection against the charged particles of the solar wind, which are what the magnetosphere deflects. They are complementary, Earth has both, and both matter for life, but they are entirely different mechanisms operating on entirely different threats. A planet could have one without the other. Earth, fortunately, has both, and the accident of having both is one of the reasons you are here. The stakes of the geodynamo become fully legible only when you look at a planet that lost its version of this engine, Mars. Mars is not a hypothetical. It is not a thought experiment. It is a real world, our nearest neighbor, at its closest, a planet that formed from the same disk of material as Earth, that once had liquid water on its surface, that once had a thick enough atmosphere to support weather, and that once had a global magnetic field embedded in its crust and presumably generated by a convecting iron core. We know this because the oldest rocks on Mars, the ancient terrain of the southern highlands, preserve remnant magnetization. Tiny magnetic signatures locked into the rock billions of years ago, the same way that terrestrial lava records the Earth's field as it cools through the Curie point. Mars once had thermo-remnant magnetization being recorded in its rocks. It once had a dynamo, and then the dynamo stopped. The timing is not perfectly resolved, but the best current estimates place the effective end of the Martian dynamo around 4 billion years ago, perhaps somewhat earlier, in the violent bombardment period when the inner solar system was still being pummeled by debris left over from planetary formation. Once the dynamo stopped, whether because the core cooled too fast, or because Mars is too small to have sustained the interior heat long enough, or because the larger impactors disrupted the interior during the heavy bombardment period, the global magnetic field collapsed. What remained were patches of remnant magnetization in the old crust, fossil fields from a dead engine, unable to protect the planet, able only to create small, local magnetic anomalies that the MAVEN spacecraft has now mapped in detail. Without the field, the solar wind had direct access to the Martian atmosphere, and it has been doing what the solar wind does to an unshielded atmosphere ever since. It has been slowly stripping it away. NASA's MAVEN spacecraft, the Mars atmosphere and volatile evolution mission, has been in orbit around Mars since 2014, and one of its primary purposes has been to measure this ongoing atmospheric loss directly. The numbers it has returned are sobering in their precision. Mars is currently losing atmosphere to the solar wind at a rate on the order of 1 to 2 kilograms per second. That number shifts with solar activity. During a solar storm, the rate spikes dramatically as the more intense solar wind strips away material faster. Over geological time, the accumulated loss is enormous. The thick, early atmosphere that Mars possessed when it still had liquid water on its surface is gone. The atmospheric pressure at the Martian surface today is less than 1% of the atmospheric pressure at Earth's surface. The water that once flowed in the ancient river valleys and pooled in the early basins is either locked in the polar ice caps or was lost as water vapor, as hydrogen and oxygen ions stripped away by the solar wind over billions of years once the magnetic shield was gone. Mars is what happens when the engine stops. It is not an immediate catastrophe, it is a slow erasure. A planet does not lose its atmosphere in a year or a century or a millennium. It loses it over millions and billions of years, steady gram by gram and kilogram by kilogram, until what remains is a thin, cold whisper of carbon dioxide and nitrogen barely thick enough to register on instruments. And at the end of that process, you have what Mars is now, a cold, dry, irradiated surface, largely uninhabitable by any life resembling what we have on Earth, preserved in geological time like a warning. The comparison is not meant to frighten you, it is meant to put weight behind what the geodynamo has accomplished. The same solar wind that is stripping Mars hits the Earth every day. The same particles, the same pressure, the same slow, patient erosion. Earth's atmosphere is not being stripped because the iron engine in the outer core is still running, still generating the field, still pushing the solar wind aside. The two planets are a controlled experiment in what a geodynamo does for a world, and Mars is the control group. Now, if the magnetosphere is the shield, the question that follows naturally is, how do we know anything at all about how it has behaved in the past? The field itself leaves no direct marks on the surface. It passes through rocks and through the air and through the ocean without scratching anything. You cannot hold a piece of ancient field in your hands. You cannot dig it up. You cannot find it in a stratum and date it, but you can find its memory. You can find it preserved in the one thing that records the field with extraordinary fidelity: volcanic rock as it cools. The key is a temperature called the Curie point, or the Curie temperature. For the mineral magnetite, iron oxide, one of the most common magnetic minerals in basaltic rock, the Curie point is about 580 degrees Celsius. Above that temperature, the magnetic moments of the iron atoms in the mineral are disordered, randomized by thermal agitation, pointing in all directions and averaging out to zero net magnetization. The mineral is magnetically blind. But as the rock cools below 580 degrees, something changes. The thermal energy is no longer enough to keep the magnetic moments randomized. They begin to align with the ambient magnetic field, and the field of the Earth at that place and time. And they lock in. The mineral crystallizes into its low-temperature structure, with those moments frozen in place, pointing in the direction the field was pointing at the moment of cooling. And once cooled, once crystallized, those moments stay for millions of years, for hundreds of millions of years, for as long as the rock remains unmelted and unshocked. The mineral holds the memory of the field that was there when it cooled. So this is thermoremnant magnetization, and the science built on reading it is called paleomagnetism. Literally, the study of ancient magnetism. Every lava flow that has ever cooled on the surface of the Earth, every sill that intruded into existing rock and cooled in place, every basalt that erupted on the ocean floor and froze against the cold seawater, all of them carry this record. They are fossil compasses. They have been pointing in the direction of Earth's field at their moment of solidification ever since, waiting patiently for someone to come and measure them. And what paleomagnetic measurement of these rocks reveals, when you collect samples from different ages and different places and compare them, is one of the most startling facts about Earth's deep history. The field has not always pointed the same way. At some points in the past, a compass held over the cooling lava would have pointed not toward the geographic north, but toward the geographic south. The polarity of the field has reversed. Magnetic north has swapped with magnetic south. Not once, not twice, but hundreds of times over the past few 100 million years. The field is capable of flipping entirely. This was a strange and difficult idea when it first emerged from paleomagnetic measurements in the mid-20th century. The notion that the whole global magnetic field could simply reverse its polarity, north becoming south and south becoming north, seemed implausible. The mechanism was unclear, the timeline was uncertain, and there was no obvious record to look at. Where would you find a continuous, well-dated archive of the field's behavior over millions of years? The answer was beneath the ocean. In the early 1960s, oceanographers began conducting systematic magnetic surveys of the seafloor, dragging sensitive magnetometers behind research ships as they crossed the mid-ocean ridges, the great underwater mountain ranges that run down the center of the Atlantic and across the Pacific and Indian Oceans, where new oceanic crust is continuously being created as the tectonic plates pull apart and magma wells up from below. And when they mapped the magnetic field at the seafloor, they found something no one had quite expected. The seafloor was striped, alternating bands of rock running parallel to the ridge axis, magnetized in opposite directions, normal as the field is today, and reversed. And the stripes were symmetric. On either side of the ridge, the pattern of normal and reversed bands was a mirror image of the pattern on the other side. Whatever process was creating the stripes was creating them on both flanks at the same time. The interpretation, worked out independently and in combination by Frederick Vine, Drummond Matthews, and Lawrence Morley, the Vine-Matthews-Morley hypothesis, published in 1963, was both elegant and revolutionary. The sea floor at mid-ocean ridges is being created continuously, they argued. New basaltic crust wells up along the ridge, cools, acquires the thermo-remnant magnetization of the field at that moment, and is then slowly carried away from the ridge on both sides as the tectonic plates spread apart. When the field reverses, the new crust being created at that moment acquires the reversed magnetization. When it reverses again, the new crust acquires normal magnetization again. The result, over millions of years of continuous seafloor creation and spreading, is exactly those alternating symmetric stripes. A tape recording of every reversal the field has undergone, written in basalt and spread out across the ocean floor. And because the stripes could be dated using radiometric dating of rock samples collected from the seafloor, and by comparison with known reversal timescales derived from continental lava flows, they provided not just a record of reversals, but a clock. The symmetric stripes told you how fast the seafloor was spreading. They confirmed that the continents and the ocean floor were in motion. They were, in the end, some of the most important evidence that cemented the theory of plate tectonics in the 1960s, transforming geology from a descriptive science of fixed features into a dynamic science of moving plates and reshaping continents. All of this in the entire edifice of plate tectonics, the understanding that the surface of the Earth is a mosaic of moving slabs rearranging themselves over millions of years, rests in part on the fact that lava records the magnetic field as it cools, and that the field sometimes reverses. The geodynamo's reversals were not just an interesting anomaly. They were the key that unlocked the architecture of the planet's surface. The seafloor stripes gave scientists something else, a detailed timeline of when reversals happened. And one of the most important facts that timeline reveals is that reversals are not rare. They are not anomalies. They are not catastrophes that shake the planet and leave marks in the fossil record. They are normal recurring events in the life of the geodynamo, and they have been happening regularly, with enormous variability in the intervals between them, but regularly in the sense of repeatedly, throughout geological time. That timeline and what it reveals about the behavior of the geodynamo is where the next part of this story begins. But for now, hold this thought. The seafloor is a library. Every stripe of basalt running parallel to every mid-ocean ridge, somewhere below the cold, dark water, is a page in a book that took hundreds of millions of years to write, and we can read it. We can read it because an iron mineral cools through 580 degrees and stops being blind, because the engine in the outer core changes its mind from time to time about which way to point, and because human beings in the middle of the 20th century dragged magnetometers across the ocean floor and noticed something strange and thought carefully about what it meant and arrived at the truth. The field is not fixed. It never has been. And understanding how it moves and changes and sometimes very nearly falls apart altogether is the next layer of this story. The layer where the reversals become real, where the near collapse 42,000 years ago leaves its mark in ice cores from Greenland and lava from a chain of volcanoes in France, and where the past becomes a guide to what the engine is doing now and what we should and should not fear from the changes currently underway. But before that, it is worth pausing a moment in what paleomagnetism actually represents. We drill a core of basalt from an ancient lava flow. We take it to the laboratory. We put it in a magnetometer that can measure the direction of its remanent magnetization with extraordinary precision, down to fractions of a degree. And we find that 500,000 years ago, or 5 million years ago, or 50 million years ago, the rock we are holding in our hands was lying on the surface of the Earth in different geography, and the field at that moment was pointing in a particular direction, and the mineral magnetite in the rock captured that direction and has held it faithfully ever since. We are reading a message left by the planet's interior, written in the language of atomic magnetic moments, preserved across millions of years of geological time. It is an extraordinary act of preservation. The fossil record decays, soft tissue disappears, even bone turns over, substituting minerals, changing slowly over millions of years. But the thermo-remanent magnetization in undisturbed basalt is astonishingly stable. The magnetic moments locked in at 580 degrees do not drift significantly over geological time. They are still pointing where they were pointing on the day that rock cooled, give or take small secondary overprints that careful laboratory treatment can identify and remove. The rock remembers, and the memory extends very far back. Paleomagnetic studies of ancient continental rocks have pushed the record of the geomagnetic field back to timescales measured in billions of years. The field has been running in some form for at least 3.5 billion years. Some researchers working with ancient zircon crystals from sites like the Jack Hills of Western Australia have argued that evidence for a field exists even earlier, perhaps 4.5 billion years ago, close to the formation of the Earth itself. Though these older results are more contested, the zircons having had a complex history that may have reset or partially overprinted their original magnetization. The safe consensus is that the geodynamo has been operating and generating a field for at least 3 to 4 billion years. Through almost the entirety of Earth's biological history, from the first single-celled life in the ancient ocean to everything alive tonight, the engine has been running. That is an almost incomprehensible duration. The sun will exhaust its hydrogen fuel in about 5 billion more years. The geodynamo has already been running for perhaps 3/4 of that span. It has outlasted the formation of the moon. It has outlasted the late heavy bombardment. It has operated while life assembled the first eukaryotic cells, while multicellular life evolved, while animals colonized the land, while dinosaurs came and went, and mammals inherited the surface. Throughout all of this, the iron engine turned and the field held and the solar wind was deflected and the atmosphere was preserved. This is what the frozen record in ancient rock reveals. If you sit with it long enough and feel its full weight, not just data, not just a timeline of reversals and excursions, but evidence that this planet is, in some fundamental sense, alive in its interior, running a machine so robust that it has persisted for billions of years through bombardment and cooling and whatever turmoil the deep Earth has undergone. And that the air you are breathing tonight, the atmosphere outside the window, the water in the oceans that made all the rest possible, these are the legacy of that engine's persistence. The seafloor carries the most recent pages of that record, and they are detailed enough to tell us not just that reversals happen, but precisely when the last several hundred of them happened. They are detailed enough to let us count the intervals between reversals, to notice that some periods of Earth history were dominated by frequent flipping, while others saw the field hold its polarity for extraordinary stretches of time. They are detailed enough, in the end, to tell us something very specific about the most recent chapter in this story. what the field has been doing in the last few 100,000 years and what it is doing right now. And that specific recent chapter, the last full reversal, the near collapse 40,000 years ago, the strange growing hole in the shield over the South Atlantic, and the North Magnetic Pole currently racing towards Siberia faster than it has moved in recorded history. That is where this account is going next. The seafloor has told us that the engine breathes, the lava flows have told us that it sometimes nearly stops. The satellites in orbit right now are telling us something is changing slowly in ways we can measure and track, and, if we read carefully, understand without fear. Everything that comes next is already in the rock, waiting to be read. There is a particular chapter in the seafloor record that geologists call the Brunhes-Matuyama reversal, and it is, in a quiet and rather profound sense, the boundary between a different world and this one. It happened roughly 773,000 years ago, perhaps 780,000. The precise figure depends on which dating method you trust and which study you read most recently, and careful scientists will give you a range rather than a single number because honesty about uncertainty is part of how the science keeps itself clean. But somewhere in that neighborhood, in a period of Earth history so distant that our entire genus was only just beginning to explore the use of fire, the magnetic field that had been pointing in one direction for an enormously long time, slowly, fitfully, over the course of perhaps 1,000 years or perhaps as many as 22,000, the estimates vary considerably and the argument is still ongoing, reorganized itself into something unrecognizable, wandered through a phase of complex, multipolar confusion, and then settled again pointing the other way. North became south, south became north, not suddenly, not with a crack or a flash or any event a living creature could have perceived. The field weakened first, as it always does during a transition, dropping perhaps to 10% of its normal strength. The single clean dipole, the bar magnet shape that we call normal, dissolved into something messier, a field with several weak poles distributed unevenly around the planet, none of them dominant, none of them stable. If a compass had existed in those years, and if some patient observer had stood in one place and watched it for century after century, they would have seen the needle wander with no settled direction, drifting slowly, pointing somewhere and then somewhere else, tracing a gradual arc across the sky that had no obvious destination. And then, over more centuries, a new dominant orientation would have begun to assert itself, strengthening gradually, the multipolar tangle resolving back into something dipole-like, but reversed. The needle would have found south where it had always found north. The field, since that reversal, our field, the one whose lines of force the migratory birds navigate by, and whose fringes light up green and red at the poles, this field is called the Brunhes-Chron, named for the French geophysicist Bernard Brunhes, who in 1906 was among the first to recognize that ancient volcanic rocks could preserve the direction of the field at the time of their cooling. The Matuyama Chron preceded it, a long stretch of reversed polarity named for the Japanese scientist Motonori Matuyama, who in the 1920s mapped the polarity record in rocks across the Pacific. Together their names mark the boundary, the moment of transition that separates our normal period from the reversed one before it. We have been in the Brunhes-Chron for nearly 800,000 years. That is longer than Homo sapiens has existed as a species. And here is something worth letting settle for a moment. That reversal was not the first, and it was not exceptional. The seafloor record, read carefully over its full length, reveals that the field has reversed its polarity hundreds of times over the course of Earth's history. Hundreds. Some periods saw reversals arriving relatively frequently, every 100,000 years or so. Others were quieter. But the reversals themselves are not rare. They are not catastrophic exceptions to a normally stable state. They are part of the engine's ordinary deep time behavior, a recurrence that has been woven into the planet's operation for as long as the geodynamo has run, and the intervals between them are, crucially, not regular. This is a point that deserves to be stated carefully and clearly because there is a persistent and rather stubborn misconception that the field operates on a schedule, that reversals arrive at predictable intervals, that there is some kind of geological clock ticking away in the deep Earth, and that by measuring how long it has been since the last reversal, we can determine whether we are overdue for the next one. We are not overdue for anything. The concept of being overdue applies to events that follow a regular pattern. Buses on a timetable, heartbeats, the orbit of a moon. Reversals are not like that. The intervals between them are irregular to a degree that makes the word schedule meaningless. Some reversals are separated by tens of thousands of years, others by tens of millions. The field does not count time between flips and flip again when the count reaches a predetermined number. It does what the fluid dynamics of a vast, churning, enormously complicated ocean of liquid iron tells it to do, and the fluid dynamics of that ocean are governed by processes. The rate of heat loss from the core, the interplay of thermal and compositional convection, the subtle effects of the mantle above and the solid inner core below, that do not organize themselves into anything as tidy as a clock. The most dramatic illustration of this irregularity is a feature of the record known as the Cretaceous normal superchron. It is sometimes called, for reasons that will become obvious, the Cretaceous quiet zone. For roughly 37 to 40 million years, a stretch of time so immense that it is genuinely difficult to hold in the mind, the field did not reverse at all. From approximately 120 million years ago to approximately 83 million years ago, during the age when dinosaurs were at their most diverse and the first flowering plants were beginning to spread across the continents, the geomagnetic field simply held its polarity. The engine ran, the shield functioned. The field may have fluctuated in strength, may have developed local complexities at its fringes, but the grand north-south orientation of the dipole, the fundamental direction the compass would have pointed, remained stable for 40 million years. No one fully understands why. The conditions in the core during that period were presumably different in some way from the conditions that produce more frequent reversals, but the exact nature of that difference is still a subject of active investigation. It may have had to do with the rate at which heat was escaping through the mantle above. It may have involved changes in the pattern of mantle convection that altered the thermal boundary conditions at the core's surface. It may reflect something about the state of the solid inner core itself during that period. The honest answer is that we are still working it out, and the superchron remains one of the more wonderful open questions in deep Earth physics. What it does emphatically is kill the idea that the geodynamo runs on any kind of predictable schedule. A system that can hold its polarity for 40 million years and then shift into a phase of relatively frequent reversals is not a system with a timetable. It is a system with a character, complex, variable, responsive to conditions that change over geological time. And it is precisely that character that makes it so interesting to study. The Brunhes-Matuyama reversal, when it eventually came, represented the end of an interval during which the field had been in its current normal orientation for a reasonably long time by historical standards. We have now been in this orientation for nearly 800,000 years. That is not unusually long. The Cretaceous superchron alone lasted 50 times as long. There is no reason to regard our 800,000 years as a warning, as a countdown nearing its completion, as evidence that a reversal is imminent or inevitable or overdue. What there is reason to pay attention to, and what the record genuinely does tell us, is how a reversal unfolds, what the transition looks like, what it means for the shield during the years it takes to complete, and whether any event in the recent geological past has given us a sense of what that experience was actually like for the living world. For that, the most remarkable chapter in the record is not a full reversal at all. It is something shorter, stranger, and, in some ways, more instructive. About 41,000 to 42,000 years ago, in the cold of the last ice age, while Neanderthals were still present in parts of Europe and modern humans were spreading through new territories, the geomagnetic field did something that looks, in retrospect, like a reversal that changed its mind. The dipole weakened dramatically. Within what may have been a relatively short period of time, centuries, not millennia, the field strength collapsed to something like 5% of its present value. The poles, such as they were, wandered. The orderly dipole dissolved into complexity. And then, before any stable reversed polarity could establish itself, the field reversed again and strengthened back towards something resembling its original orientation. It was, in the language of paleomagnetism, an excursion rather than a reversal. The field swung out of its lane, wobbled severely, and came back. The whole event lasted perhaps 1,000 years in its most intense phase. And then it was as if it had almost happened. This event is called the Laschamp excursion, named for the place where its signature was first clearly identified. The Laschamp lava flows in the Chaîne des Puys, a chain of young volcanoes in the Auvergne region of central France. The lava had cooled through the Curie point during those extraordinary centuries, and the magnetic minerals in the basalt had locked in a record of the field's wild departure from its normal orientation. When geologists analyzed those rocks, they found something that should not have been there: a strongly anomalous magnetic direction preserved in the cold stone, pointing the wrong way. And the evidence for the Laschamp does not rest on those lava flows alone. There is independent confirmation of a different kind and from a different archive that makes the event's reality essentially certain. When the magnetic field is weak, it provides less resistance to the stream of energetic particles that arrives from beyond the solar system, what physicists call cosmic rays. These particles are always present, always arriving, always attempting to penetrate the magnetosphere. Normally, the field deflects the majority of them, but when the field collapses to 5% of its strength, something like the Laschamp, the deflection fails in large measure, and the high-energy particles flood more freely into the upper atmosphere. When cosmic rays hit the upper atmosphere, they trigger reactions that produce certain rare isotopes. Among them, beryllium-10, a form of the element beryllium that does not occur in significant quantities by other means, and whose presence in any given layer of ice or sediment is a direct signature of how much cosmic radiation was striking the atmosphere at the time of that layer's formation. Drill into an ice core from Greenland or Antarctica, extract the ice laid down 41,000 years ago, and measure the beryllium-10 in it, you find a spike. A clear, unmistakable spike centered on the period of the Laschamp that independently confirms that the field was dramatically weakened at that time and that the cosmic ray flux was correspondingly elevated. Carbon-14, the radioactive isotope used in radiocarbon dating, is also produced by cosmic ray interactions in the atmosphere, and its concentration in the atmosphere and in organic material from that period shows a similar signature. The ice and the sediment and the volcanic rock all agree. The field nearly failed, the shield briefly buckled. The Laschamp excursion is as well confirmed as anything in the paleomagnetic record. What the excursion meant for the living world during those centuries is a more complicated question, and one that sits at the edge of what the science has established versus what it is still actively working out. In 2021, a team of scientists led by Alan Cooper and Chris Turney published a paper in the journal Science proposing what they called the Adams event. The idea was this: that the dramatic weakening of the field during the Laschamp excursion and the corresponding surge in cosmic radiation had caused significant environmental disruption, changes in atmospheric chemistry, including the ozone layer, increases in ultraviolet radiation reaching the surface, alterations to climate, and that these disruptions may have contributed to a cascade of ecological changes around 42,000 years ago. The paper pointed to the apparent timing of megafaunal extinctions in Australia and other regions, the disappearance of the Neanderthals from Europe, and saw in a detail that has caught a great deal of public attention, a remarkable flourishing of cave art and the expanded use of red ochre pigment, which the authors suggested might reflect human populations seeking shelter underground and adapting their behavior in response to a more hostile surface environment. It is a striking and imaginative hypothesis. It is also, and this must be said clearly, a contested one. Other scientists have questioned the strength of the proposed connections, arguing that the timing of the extinctions and the Neanderthal decline does not align as cleanly with the Laschamp as the hypothesis requires, and that the evidence for the specific causal chain from field weakness to ozone depletion to ecological collapse is not yet robust. The hypothesis remains alive in the literature and may well generate productive investigation, but it has not achieved consensus. It is an open question, not a settled answer, and it should be held that way as a fascinating possibility that the science is still examining, not as an established fact about what the Laschamp did to life on Earth. What can be said with confidence is that the living world continued. The biosphere survived the Laschamp excursion, as it has survived all previous reversals and excursions we can identify in the record. Whatever disruptions occurred, and some disruptions were surely real, given the demonstrated increase in cosmic radiation, they did not end the project. Life adapted, or was resilient enough to endure the centuries of reduced shielding, or found other protective mechanisms sufficient to weather the storm. The atmosphere itself, even at 5% field strength, provides considerable protection against the full force of cosmic radiation. The field is one layer of the shield, but it is not the only one, which brings us to the present. We live in a field that has been weakening, measurably, consistently, and over the full period for which we have reliable instrumental measurements, which begins in the 1840s when the German mathematician and physicist Carl Friedrich Gauss developed the first quantitative methods for measuring the strength and direction of the magnetic field, and began the systematic global observations that gave us our first true baseline. Since those measurements began, the overall strength of the dipole field has declined by roughly 9%. 9% in roughly 170 years. That is a real change, large enough to measure confidently, observable in the data from ground stations distributed across the planet and confirmed by the satellite measurements that have become available more recently. And somewhere in the South Atlantic, this weakening is not evenly distributed. There is a region, large, persistent, and growing, where the field is not merely a little weaker than average, but dramatically, strikingly anomalous. It extends over much of the South Atlantic Ocean and into parts of South America, and at its center, the field is weak enough that the inner radiation belt, the inner of the two Van Allen donut shapes that normally sit comfortably far above the surface, dips down close to Earth as low as 200 kilometers in altitude, where satellites and spacecraft actually travel. This region is the South Atlantic Anomaly, and its existence is not theoretical or speculative. It has consequences that engineers and mission planners must account for routinely, because any spacecraft that passes through the South Atlantic Anomaly is flying through a zone of elevated radiation, elevated because the inner Van Allen belt has descended to orbital altitude there, bringing its trapped energetic particles into the path of anything that happens to be crossing that region of sky. The Hubble Space Telescope, one of the most precisely engineered scientific instruments humanity has ever built, stops taking science observations every time it passes through the South Atlantic Anomaly. Not because of any mechanical failure, and not as a precaution against some hypothetical future risk. It stops observing because the radiation environment inside the anomaly causes cosmic ray hits that corrupt the data from its detectors. The operators close the instruments, wait for the spacecraft to cross through and emerge on the other side, and then resume observations. This happens on every pass. It has been happening for decades. The astronauts aboard the International Space Station, which also crosses the anomaly in its orbit, receive higher radiation doses during those passes than at other points in their trajectory. This is tracked, it is managed, it is one of the routine operational realities of long-duration spaceflight, not a crisis, but a persistent condition that reminds anyone paying attention that the shield is not uniform. The South Atlantic Anomaly appears to be connected to a region of anomalous magnetic behavior on the core mantle boundary beneath southern Africa, a patch where the field's direction is actually reversed relative to the normal orientation of the dipole, a so-called reversed flux patch that affects the configuration of the field at the surface above it. Data from the ESA's Swarm constellation, 3 satellites launched in 2013 specifically to map the fine structure of the magnetic field and its changes over time, suggests that the anomaly is not static. It appears to be growing in extent and, in recent years, to be splitting into 2 distinct lobes, as if the reversed flux structure in the core below is developing internal complexity and spreading. What this means in the long run is genuinely uncertain. It may be that the South Atlantic Anomaly is a transient feature, a regional fluctuation that will gradually resolve as the core flow patterns that produce it shift over decades or centuries. It may be an early signature of something more significant happening in the core. The swarm data is accumulating, the models are improving, and the scientists studying it are carefully reluctant to overstate what can be concluded from observations that, however detailed, cover only the last few decades of a process that operates on timescales of thousands to millions of years. Meanwhile, elsewhere on the planet, the magnetic North Pole has been moving. Magnetic poles have always moved. The geomagnetic field is not static even in quiet periods. It drifts, it varies regionally, it shifts gradually in response to changes in the pattern of flow in the outer core. The North Magnetic Pole, which is the point in the northern hemisphere where the field direction is vertical, straight down into the Earth rather than at any horizontal angle, has been wandering around the Arctic for as long as we have been tracking it. Throughout most of the 20th century, it drifted across the Canadian Arctic at a rate of perhaps 10 or 15 kilometers per year, a drift that was noticeable and measurable but not dramatically alarming. Then sometime in the 1990s something changed. The drift accelerated. By the early years of this century, the North Magnetic Pole was moving at something approaching 50 or 60 kilometers per year, several times faster than its historical average. And the direction of that motion had shifted. Instead of wandering aimlessly within the Canadian Arctic, it was now moving purposefully northward and then veering towards Siberia, as if some change in the underlying flow pattern in the outer core had given it a new destination. The practical consequences of this motion are not merely academic. The World Magnetic Model, the mathematical representation of the Earth's magnetic field that is used by smartphones and aircraft navigation systems and ships, and the military to convert between magnetic and geographic bearings, this model is updated every 5 years to account for the field's gradual changes. But the acceleration of the pole's drift was so significant that the model, updated on schedule in 2015 and designed to remain accurate until 2020, was already drifting outside acceptable accuracy tolerances for navigation before that 5-year period was up. An unscheduled update was issued in 2019, the first time such an early correction had been required. The pole was moving faster than the model's designers had planned for, All of this, the 9% weakening of the dipole, the growing South Atlantic Anomaly, the racing North Pole, the swarm mission and its detailed and slightly unsettling maps, is real and measurable and worth understanding clearly. And the honest understanding is this: none of it means the field is dying, and none of it means a reversal is imminent. The 9% decline in dipole strength, placed in the context of the paleomagnetic record, describes a field that is still well within the normal range of variation observed throughout the Brunhes chron. The field has been weaker than this before, during the Brunhes, without reversing. It has also been stronger. The long-term average strength of the field over geological time is actually lower than its 20th century value, which means the current level, even after the weakening, is not anomalously low by historical standards. It may simply be returning toward a more typical value after an unusually strong period. And the pole drift and the South Atlantic Anomaly and the weakening are all real phenomena that deserve study and monitoring, but they do not constitute a countdown. Reversals are aperiodic. The field's current behavior does not trigger any clock. There is no threshold at which weakening automatically becomes reversal. The engine in the outer core may continue in its present orientation for another 100,000 years, or another million. It may shift into an excursion, a Laschamp-like dip and recovery without completing a full reversal. Or it may, at some point in the future, work its way through a full transition. All of these are possible, and none of them is imminent in any sense that a human lifetime or many human generations could witness. What would a reversal actually mean if one did eventually occur? The honest answer, the one the science actually supports, and that the popular imagination consistently distorts into something more dramatic than it is that a reversal would be technologically disruptive and scientifically fascinating, and not an extinction event. The field during a transition does not vanish. It weakens and becomes complex, as we have discussed. But even at its weakest, in a full reversal transition, it retains some structure, some capacity to deflect charge particles, some residual contribution to the magnetosphere. And the atmosphere, with the column of air above the surface, tens of kilometers thick, is itself a substantial shield against both particle radiation and ultraviolet light. It was the atmosphere, not the magnetic field, that protected the first single-celled organisms for the first 2 billion years of life on Earth, in the period before the geodynamo was reliably operating in its modern form. The magnetic shield and the atmospheric shield are complementary, and the atmosphere does not switch off during a reversal. The real practical vulnerabilities that a reversal would create are modern ones: satellite infrastructure damaged by elevated radiation during the extended transition, GPS and navigation systems disrupted by the complex multipolar field that would make accurate magnetic reference unreliable, power grids potentially vulnerable to the kind of induced currents that solar storms already occasionally threaten them with, airline passengers and crew on high-altitude polar routes receiving higher radiation doses, and astronauts in space requiring more careful management of their cumulative exposure. These are serious technological concerns, and a civilization that depends as thoroughly on satellite-based systems as ours does would face real challenges during a transition that lasted thousands of years. But none of this is extinction. The fossil record of past reversals, read over the full sweep of Earth history, during which hundreds of reversals have occurred, does not show a reliable correlation with mass extinction events. The great extinctions, the end Cretaceous event that took the non-avian dinosaurs, the end Permian event that came close to ending all multicellular life, happened independently of the reversal record, driven by impacts and volcanism and the internal chemistry of the ocean and atmosphere. Life has lived through hundreds of field reversals and is evidently sufficiently resilient to do so, which is perhaps the most quietly reassuring fact that the entire record has to offer, The engine has been running, reversing, recovering, and running again for at least 3.5 billion years. And through all of that time, through supercrons and frequent reversal periods, through Laschamp-like excursions and full transitions, the biosphere has persisted. There are even now things about the engine that we have not yet fully understood, and one of the most intriguing is something that happens not at the surface, but at the very center of everything. The solid inner core, that sphere of compressed iron roughly the size of Pluto, as hot as the sun's surface yet held solid by the crushing pressure of everything above it, may not be moving at exactly the same angular rate as the rest of the planet. Seismologists have long suspected that the inner core rotates slightly differently from the mantle and the crust, a phenomenon called inner core superrotation, with the inner core gaining fractionally on the outer layers and slowly turning relative to the surface. The first clear evidence for this came in the 1990s when researchers noticed subtle differences in the travel times of seismic waves passing through the inner core from different directions and at different times. Differences that could be explained if the crystal structure of the inner core was rotating relative to the observation points at the surface. In 2023, a study by Yi Yang and Xiaodong Song, building on decades of accumulated seismic data, proposed something stranger still, that the inner core's rotation relative to the surface had not merely been slowly drifting, but had actually paused sometime around 2009 and may have since begun rotating in the opposite direction relative to its previous motion, oscillating back and forth on a cycle of roughly 70 years. The 2023 paper attracted considerable attention and considerable scientific debate, and it is probably best understood as a provocative hypothesis that opens a genuinely important question rather than as a settled conclusion. Other researchers have proposed alternative interpretations of the same seismic data. The argument continues and will continue until the data are either confirmed by more observations or the alternative explanations are rigorously tested. But the possibility itself is remarkable. A solid ball of iron, 1,220 kilometers in radius, quietly turning at its own pace inside the rotating ocean of liquid metal that surrounds it, and perhaps periodically reversing the direction of that relative turning. This is the kind of internal complexity that a planet keeps hidden from everything above its surface, accessible only through the indirect language of seismic waves. There is more. Seismologists studying the finest details of how seismic waves behave as they cross the innermost portions of the inner core have in recent years proposed the existence of what they call the innermost inner core, a distinct ball roughly 600 kilometers across at the very center of the inner core itself, with a different alignment of its iron crystals from the rest of the inner core. If this is real and the evidence is still being evaluated, then the Earth's center has a structure within a structure, a core within the core, a kernel at the heart of the kernel, each layer with its own subtle properties, its own response to the pressures and temperatures that prevail there. And the question of when the inner core began to form is itself unresolved. The current estimates range widely, perhaps as recently as 500 million years ago, perhaps as long as 1.5 billion years ago. The uncertainty is large because we cannot directly observe the evidence. We infer the inner core's age from models of the Earth's thermal history and from features of the paleomagnetic record that might reflect a change in the dynamo's energy source when solid iron began to crystallize out for the first time and compositional convection began to supplement thermal convection. There may even be a moment in the paleomagnetic record where the field strengthened or became more stable as the inner core began to provide its contribution. But identifying that moment clearly in the ancient record, amid all the noise and complexity of several billion years of geological overprinting, remains a challenge that keeps researchers busy. What is certain is that the engine we live above is far richer and stranger than any simple description of it captures. It is a fluid system with a solid heart, a solid heart that may be developing structure within itself, an outer ocean organized into column-like flows by the planet's rotation, a heat budget fed by the slow snow of iron crystals settling toward that growing inner sphere, and the buoyant exhalation of lighter elements rising through the fluid above. It has run in broadly recognizable form for billions of years, surviving the slow cooling of the planet, the bombardment of early Earth, the gradual changes in mantle convection that have altered its thermal environment. It has flipped and recovered. It has held still for 40 million years. It has nearly collapsed and then rebuilt itself. And it is, in the end, why you are here. Not in some vague or approximate sense, but specifically and consequentially. Mars and Earth began as similar worlds. Both were warm, both had liquid water in their early histories, both sat in the habitable zone of a young star. Mars had an interior that generated a magnetic field, evidence for which is still frozen in the ancient crust of the southern highlands. Rock magnetized billions of years ago by a field that has since gone silent. But Mars is a smaller world, and small worlds cool faster than large ones. And sometime around 4 billion years ago, the Martian dynamo died. The interior lost the heat that had been driving it. The liquid metallic core solidified or became otherwise unable to sustain convective flow, and the geodynamo went quiet. And without the geodynamo, the solar wind was able to do what the solar wind does to an unshielded planet: strip away the atmosphere, particle by particle, ion by ion, at a rate that is slow by human standards, but relentless over geological time. The NASA MAVEN mission, which has been measuring Mars's atmospheric loss since 2014, has given us a number to put to this relentlessness. Mars is currently losing somewhere on the order of 1 to 2 kilograms of atmosphere to space every second. Every single second as you lie here, as the house settles around you and the night outside holds still, Mars is losing a kilogram or two of its air to the solar wind. Over 4 billion years, that adds up. The thick, early Martian atmosphere is gone. The liquid water that once pooled in its lowlands and carved its valleys has gone with it, evaporated or frozen, stripped of the blanket that kept it stable, lost to space, or locked as permafrost beneath a surface scoured by ultraviolet light that nothing shields against. Mars is a desert, not because it was born one, but because the engine inside it went silent. Earth's engine has not gone silent. It is running right now beneath you, through the floor, and down through the solid rock of the crust and the mantle, and into the outer core, where the liquid iron moves in its vast, slow, rotation-organized columns. It is producing the billion amperes that circulate through the core and generate the field that fills space around the planet to its bow shock, nearly 90,000 kilometers away on the sunlit side, where the supersonic solar wind is brought abruptly to a halt. The shield is asymmetric and imperfect. It has a hole over the South Atlantic large enough to trouble the Hubble telescope. Its north pole is racing toward Siberia at 50 or 60 kilometers a year. Its dipole is 9% weaker than it was when Gauss first measured it. And it is still there. It has always been there in some form for longer than complex life has existed on this planet. Every animal that has ever moved through air or water has done so within the protection of this field. Every bird that has ever navigated by the invisible architecture of magnetic field lines has relied on the engine's persistence. Every moment of evolutionary complexity, every clade that diversified and radiated and found new ways to inhabit the world, all of it has unfolded inside the shield. The engine is not a background condition, it is the precondition. You cannot fully account for why Earth is alive, and Mars is not without accounting for this, that something in Earth's interior has kept the fluid iron moving, kept the convection going, kept the self-exciting loop of current and field and current running for long enough that everything we call life has had time to become what it is. The bacteria, The algae, the ferns, the insects, the fish that learned to breathe air, the mammals that grew warm and complex and eventually curious, all of them lived inside the shelter of this iron engine's work. None of them knew it. They did not need to. The shield was simply there, doing what it has always done, while life got on with the business of living. Tonight, it is still there, doing what it has always done. The outer core is moving. The talar columns are turning. The light elements expelled by the slow crystallization at the inner core boundary are rising through the liquid iron above. The currents are circulating. The field lines arch through space, invisible and immense, reaching past the orbit of the moon on the night side, fending off the solar wind on the day side, funneling a fraction of the particles that slip through down into the polar atmosphere, where they excite the oxygen and nitrogen into those slow, cold curtains of green and red light that have been falling for as long as there have been eyes to see them. The record is in the rock. The stripes are in the seafloor. The Laschamp signature is in the ice, and the beryllium-10 spike tells us when the shield thinned and by how much. The Brunhes-Matuyama boundary is a line in the lava, and on one side of it, north was north, and on the other side, north was south, and the world continued either way. The Cretaceous superchron is 40 million years of quiet in a record that has known plenty of noise, and we do not yet know why it was quiet for so long, and that not yet knowing is not a failure but an invitation. The invitation that every open question in science extends, to keep looking, keep measuring, keep asking what the rock and the ice and the seismic waves are telling us. Somewhere deep in the crust of Mars, the magnetized rock of the ancient southern highlands still holds its record of a field that existed and then stopped. It is the archive of a dynamo that ran for a while and then did not. Read against Earth's record, it is the most compelling testimony we have for what the geodynamo is worth. Not in any abstract sense, but in the concrete, specific, irreplaceable sense that one of these planets has a living biosphere and abundant liquid water and an atmosphere thick enough to breathe, and the other one is a cold desert being slowly dissolved by the wind from the sun. The difference is the engine. Rest here if you are ready. There is nothing more to resolve tonight. The machine is running. The field is there. The North Pole will be somewhere in the Arctic when you wake, a little closer to Siberia than it was yesterday, still exactly where navigation systems know to find it, still doing what magnetic poles have always done in a planet that is alive and churning and old. The solid heart at the center is hot and still, under pressure that makes every other pressure in human experience seem trivial, slowly growing as the planet loses heat, and iron continues to settle and freeze and add to the inner core's mass, grain by grain, century by century. If you find yourself in the southern latitudes one day, and perhaps in Argentina, perhaps somewhere over the open South Atlantic, look up on a clear night, if the sky allows it, and know that above you the inner Van Allen belt dips lower to the ground than anywhere else on the planet, that the field is thinner there, and that the Hubble telescope was closed at that very moment, waiting to emerge. It is not frightening. It is the engine breathing in an uneven rhythm as it has always breathed, as it will continue to breathe long after any satellite we have yet built has fallen silent. The seafloor knows all of this. It has been writing it down for hundreds of millions of years in stripes of black basalt that alternate like the pages of a book. And the lava of the Chaîne des Puys, cooling 42,000 years ago in the warmth of its own eruption, set its compass needle toward a sky that was briefly wild with aurora, a sky where the field had buckled and the cosmic radiation was high, and the world below was cold and uncertain. And then the field came back, and the lava cooled. And the record was sealed. It is an old story, it is still being written. If you feel moved to share where you are listening from tonight, what country, what city, what dark room or quiet hour the night has brought you to, I would genuinely like to know. The comments are there and I read them. There is something fitting about locating yourself on the surface of a planet whose interior is still largely unknown to us, above an ocean of liquid iron moving in the dark, inside a shield that reaches to the edge of what we call near space. You are somewhere specific. The field passes through you as it passes through everything. You have done enough for one night. History will still be here in the morning. For now, rest.